So today we are going to see data transmitted from ARM Cortex processor to DS1307 using I2C bus. As I have told, the DS1307 is a real-time clock device, and in its register from 0 to 6 is used for storing the value of time and date, and this address is for second, and this address is for minute, this is hour, this is for hour, this is for day, this is for date, this is for month, and this is for year. Okay, so we are going to send this binary in the form of binary. We are going to send bit by bit. Okay, so let's write the code, and so I'm including the Java that ARM Cortex based microcontroller library. Okay, and then this one is address. Okay, I'm defining GRX68 for that DS1307. Here we are using a slave device. This is initialization of I2C. I will explain it later. And this one is the function that send the address and data bits. I will explain this later. It takes the slave address, memory address, fast memory address, and then the data to be transmitted. Okay, I will explain these two functions later. First, let's write the main called main functions. Let's take array of name time data set containing 7 values, and so here let's take the values of this. Let's take these values, because today is 14 June, Sunday. Year is 2026, and this one is not exact timing. Let's take these values. So these values are GRX55. Let me copy. 13 0x01. we will write some line of code here, but before it, let me write the initialization I2C initialization functions, because I'm going to call that functions here. So let me write this code first. So here system control is using I2C GPIO. Let's take it port A. Okay. So what does this register is use the this register, and system control is using this register, and this register is saying you supply a clock source to the bit 0 to 7 in order to choose a particular port you like. So 0 is this, and this one is bit 1, so we are setting bit 0, so we are supplying clock source to bit 0, so we are selecting GPIO A or port A. And then system control is choosing RCTC I2C register, and so this register is saying supply a clock source to the bit 0 to 3 in order to choose a particular I2C versions you want to use. That means this one. In this bit 0 to 3, you supply you're supplying 0x02, so 0x02 in hexadecimal is 0010, so 0010, so you are setting the bit 1, that is I2C1, so you are choosing I2C1 in your code. And as I have chosen GPIO A, so let's set up something here. FSEL equal to 0 x C0. C0 means 1100 000. Okay. So as I have chosen GPIO A port A, so in port A the 6-bit and 7-bit I'm choosing as alternate functions, so that I can use it for any stuff like for I2C or anything, but here I'm using I2C. It can be for SPI, anything. And here I'm clearing the bit. This particular bit 6 and 7 we have chosen, and so I'm clearing this bit so that there is no dummy data, so that it can be used newly as here I'm setting this particular bit that we have chosen, that is bit 6 and 7 we have chosen right. It has 3 according to this port control register, because if I put value 3 here, setting it value 3 here for 7 bit, then it will be for I2C SGA line. And if I put a value 3 here, then it will be in this bit, then it will be for I2C SCL line. According to this port control register, it can set for I2C or GPIO or okay PWM, but 3 is value for I2C, so I'm putting the 3. Okay, twice. Then here I'm making that particular bit for digital, that I have chosen this bit now. I'm making it digital, as I'm not choosing for analog, and most of the are operate in as digital. And ODR means I'm choosing only this bit, because I guess this and 0 is this. I is a bit. I means this 7 bit. This 7 bit is for I have set that 7 bit to 3. That means it is for SGA line. Okay, according to this port control register, setting the particular bit 7 to a value 3, that means it is for SGA line, and SGA line is the line where we have to send all those bit of address and data. So we are setting this bit. This bit is sending through SGA line, right? So sometimes we are multiple master is in rare case or exceptional case is allowed to transmit or share the I2C bus. So in ODR, open drain system, the device that is connected is output to low voltage operate transistor is used, and low level operate transistor is used, and so that when because that is for all device it is used, because if we use high device like having output connected to high level transistor, and then some device connected to low level transistor, then sometimes short circuit happens, and so output from the high level transistor device comes to low level transistor device output. So in that case short circuit happens. So because of that all the device are maintained to have output connected to low level transistor circuit. So that's the reason why we use open drain system. As in open drain system, all the transistor all the device output is connected to low level transistor circuit. And then X10, we are choosing a particular device as a master so that it can be used. Here we are choosing the ARM Cortex processor, and so by setting the bit 4 of this MCR register, we are choosing a particular device as the master device. Again, this particular bit D4 okay is to set the device in master mode. Okay, this okay bit D4 okay set to 1, and then MTPR okay then I2C is using MTPR and set to 7, because when set to 7 the data transmission will be in 100 kilobit per second. So we have chosen okay the particular GPIO ports. We have chosen particular I2C okay versions 1, and then as we have chosen port A, setting okay particular bit, we are choosing particular okay pin okay 6 and 7 for alternate functions, for any functions, and then clearing it so that there is no dummy data, and then setting okay that particular okay pin, this one only okay this bit also, this pin also, setting okay this particular okay pin 3 according to okay port control register, making it only for to work for I2C only, and then particular this okay bit is again okay set as digital here to do any digital okay operations, and then okay making okay this particular bit open drain system circuit, because here okay is the data is going to send, and so its output will be connected to low level like a operate transistor, and this one is not necessary because here data is not going to send. And then we are choosing like a particular device as master so that we can use in our transmission, and this is like a making data to transmit in the range of 100 kilobit per second in that speed. Okay, that is I2C initialization. And after this, okay, let's go to this function. And since I2C is initialized, okay, let's transmit the address bit and data bit. So okay, we will take select address value and memory address, and then and also we will take data. Okay, let's take a variable name here, and then now I2C is using MSA. MSA is a register, 32-bit register. I2C MSA is a 32-bit register where we used to store okay the slab address from pin number 1 to 7 only. 0 is not used because it is for to detect whether we are transmitting or receiving from the slab device. Here okay pin number 1 to 7 is only used because this is in total 7-bit and slab address is only 7-bit. So okay, since pin number okay 0 is not used, so we will write shift 1, because this is left shift, this is left shift, and this means shift left only once. That means the address okay here we are using is 68, right, and it is 7-bit, so 6 is this and 8 is 1000, right. So okay, we are shifting left, 1 means okay 0, that means this one is address, right, and we are starting from this bit, that means we are shifting left only once. Okay, that's why 1 is right here, that means only once, shift left only once. and then we will write the memory address. This is first location of the memory of select device GS1307. Okay, is actually going to be this just right as return. Okay, here this is the first memory location, right, of DS1307 and the select device. Okay, so that one, and then so I2C is now we have select address, memory address, then I2C is now using MCS register 3. So MCS register 3, as we are for the first time sending the select address to choose a particular address, that means we are writing. Writing means sending or transmitting. So this is now MCS is a register, as we are writing sending or transmitting. MCS will be now used as a write control register. Write control register. So this one is MCS is now used as a write control register. There is another MCS also there that is used as a read control register, but here we are writing, so we are using as write control register. And it says what we will write here, I think 3. So it says 3 means 1 1, right? 1 1, that means run and then start the transmission. So run and then start the transmission now. Then I have take one variable called error here. So I'm writing it here, and then wait till then. So I'm calling these functions. The functions is this one is saying run and then start the transmission. Then if the transmission is start, then the bus is busy. Bus is busy means transmission started. So I'm writing this function. So as it run and then start the transmission, the bus is going to be busy. The bus is going to be busy means transmission is started. So we will write so what is the function? So as the MCS equal to 3 means, so this bit is saying run and then start. So the transmission started, so the bus will be busy. Bus will be busy means transmission started. So the bus will be busy, so we will say while I2C1 implies MCS and 1 means busy, right? So we will say while I2C1 implies MCS. I2C is now using MCS register, and when it is busy, 1 is busy, right? So this one we are reading the bus. We are checking the status of the bus. Checking the status of the bus means we are checking means reading, right? So we are checking, we are doing reading function, so we will now use MCS as read only control register, because we are checking, we are reading. Okay, so we are doing reading function because of that. So we here 1 means busy, okay, and 1 doesn't means run. 1 is not run here, so we are reading, so 1 is busy. Okay, 1 is busy. As the transmission is started here, okay, the bus is now busy, that means transmission is going on. When the transmission is going on, we will write to check whether there is any error, right? So return MCS 0x. Okay, so while transmission is going on, that is bus is busy, we will like to check if there is any error. We are sending here slab address and memory address. Okay, we are sending here slab address and memory address. Okay, and the bus is now busy as transmission started, and then we are checking if there is any error. Okay, and if there is any error also, this line stated is saying if there is any error, and also this line is checking if the address is acknowledged, because E means E is this, right? This one is error bit, this one is address acknowledgement bit, this one is data address acknowledgement bit. This one, we are the bus is busy and we are reading. We are checking if there is any error. Okay, that means we are reading if there is any error. If any error pops up, or if address is not acknowledged, means error like that, or if address is acknowledged like that. Okay, so because we are sending that address, that slab address and then memory address, and here we do acknowledge, right? So because of that, we are checking the acknowledgement bit, if address is acknowledged or not acknowledged, like that. So if address is acknowledged, then here we are not checking data bit. Okay, so data bit will be when it is 0, it is data bit is acknowledged, so it will be 1, and then when, so we are checking address. If address is acknowledged, then it will be 0, and then error will be 1. Error will be 0 if address is acknowledged. Okay, and then that 0 is 0, and so here we are not sending data, so let it be, and we are just checking the error. So error, we are just taking the address acknowledgement bit. So 0 means address is acknowledged, and so error will be 0. There will be no 0. And if error is there, if address is not acknowledged, then it will be 1. If address is not acknowledged, then there will be error. So like that. Okay, so address is acknowledged. This bit address is acknowledged, so it will be 0. Okay, let me check it. Yeah, if 0 means address is acknowledged. Okay, sometimes if address is not acknowledged, then the error will pop up like this. Okay, and then so this line is saying, well, here the bus is run and then start. So this line is saying the bus will be busy as transmission is going on, and we will check whether the address bit is acknowledged. Okay, if not acknowledged, then error is returned. So if in case there is error, then return the error. Okay, so that's all. And then the next line will be I2C1 implies now. As we have sent the address, and address is considered acknowledged in case there is no error, so we will send the data. So MDR is a register where we used to store the data that is going to transmit. This data is 8-bit in I2C data format. So it will be stored in the 0 to 7-bit of MDR register. Let me show that. Yeah, this is MDR register where data going to send in the transmission will be stored from 0 to 7 bit only. MCS go to 5. The 5 means 101. 5 means 101. Okay, so here we are going to send the data, right? That means we are transmitting the data. That means we are writing the data. Okay, we are writing the data, so we will use this MCS equal to 5. Here the MCS register we are using is MCS write control register, as we are transmitting the data. Okay, this MCS register as write only control register. So we will use, and we will say run and then stop after sending that particular data. Okay, that means run, send the process, run the process, and then stop after sending this data. Okay, and then here we are going to send this data, and it says run and then send this data and then stop after sending this data. Okay, so it is it begin to transmit the data. and then we want to check if there is so we will as the 5-bit says run and then stop after some time. So it began to the bus is busy now. It is transmitting the data. So we will say error equal to I2C read to done. So this is transmitting the data, and as the function says that it is transmitting now all those data bit. And now if we are checking whether that data is acknowledged or not, and we can check through this E, because through this E only we are going to know whether the data is acknowledged or not, because we will also like to check whether there is error or not. If there is no error, then the data is acknowledged. If there is error, then the data is not acknowledged. And this E is 1110, and this one is data bit, acknowledgement bit, this is address acknowledgement bit, this is error. And so if address is acknowledged, then address is acknowledged when this bit is 0. So this one address acknowledgement bit is 0, address is acknowledged. And here data acknowledgement bit is 0 because data is acknowledged and we are not checking address. And here we will see the error. Since the address is acknowledged, error will be 0, and so that bit only we check. And so if there is no error, then this will return. If there is error, then address acknowledgement bit will be 1. If there is error in sending data, data acknowledgement bit will be 1, address acknowledgement bit will be 0, and the error will be 1. And so we are not checking this bit. We are checking only this bit and this bit. So if there is error, then address acknowledgement bit will be 1, and so error will be 1. If address acknowledgement bit is 0, that means data is acknowledged, then there is no error, so error will be 0. So your data is transmitted and checking if there is error or not. That means data is acknowledged. Whatever data is sent is acknowledged. And then so we are checking if there is any error or not. And then here we are the bus is busy, and we are checking if there is any error or not. And here it is checking when the transmission is going to be over. When the transmission is going to be over, we are checking. And then because sometimes so this is we are sending only one time the data. So the data is sent, and then we are just checking if there is any error or not. And this line is we are checking when the transmission is going to be over, because this bit 4 is this bit 4 is a busy bit. 4 means 6 bit, right? 40 means 6 bit is a busy bit, and when this bit is low, that means when this bit is 0, then when this bit goes low, the transmission is complete. So data transmission is finished. So this bit will become so this bit is checking, and when this bit is low, data transmission will be finished. And the next line, what we are going to write is that busy bit, when it is low, the transmission is complete. But see here, when the transmission is complete, the program should check the error bit. So we will check the error bit. We are going to check the error bit, and it also says address acknowledged and data acknowledgement bit will be set. Checking the error and will be set to this. So we will error is stored here if there is any error. So we will check the error and then set to that address acknowledged. We are setting the error to address acknowledgement bit, data acknowledgement bit, that error. We are checking if there is any error and set to address acknowledgement bit and data acknowledgement bit. If there is any error, then we are sending here data, right? So if data is not acknowledged, if data doesn't want to be received by the receiving device, then data acknowledgement bit will be 1. And here we are not checking address acknowledgement bit, as we are sending data. So only data acknowledgement bit will be checked. And after this, if address data acknowledgement bit, here we are assuming it as 1, that means data is not acknowledged, then error will be 1, and this bit we are not checking. So that means we are setting this error to this address acknowledgement data acknowledgement bit and then error bit. And so error will be set like this. This error will be set saying that there is error, as data is not acknowledged. We are just assuming. So if there is no error, then it will be set to 0 0 0 0. So there is no error, and if there is error, then return the error. Else return 0, that means no error. And so in the main program, so we take an array of 7 values, that is corresponding to all those. This is 2026, this one is June, today is that 14, 0x01 is Sunday, this is time, this is minute, this is second values. You can change it to any what you like. If you want Tuesday, then it will be Monday, then 0x02, like that. If you want January, then 0x01, Okay, you can change it to any you want. So this is just array, and then I will call I2C initialization function here. Okay, to do the I2C data transmissions, set up all those I2C process I2C initialization functions and calling, and then after that I will call I2C1. Did I write I2C1 or I2C1? What did I write? Sorry, my bad. Don't mind, okay. And then I will write the memory address. So I will just write 0, and then I will write what else, data. Then that is set, and I will call the 0 index, and like this. Okay, I'm calling this one. I'm setting up all those I2C initializations, and I'm calling this byte these functions where the slab address will be sent, this memory address will be sent, and then the data. Okay, this is the data, that means will be sent. This data means this of 0 index means this one will be sent. Okay, and this is only sending the what this one is only second value, so I will send all of it. So let's copy it. This one I will send. Okay, slab address will be not changed because it is defined here. Okay, slab address. Okay, and it is only one slab address, that is DS1307, and the memory address will be now 1. 0 means 0x00. Okay, and then 1 means 0x01. Okay, I'm writing. Okay, and this one we are sending here 1, this one, because this one is second, right, and this memory is in the second location. This one, this is fixed for second, sorry, minutes. This is fixed for minute, this is fixed for second, and that's why we write this one is that 0x00 fixed for second, this one is 0x01 fixed for minute. Okay, so whatever you send here will be the 0 index, this one will be second, whatever you send here, this one will be minute. Okay, and then we will send all of them. I just copy paste. Okay, and so this one will be slab address is only one slab address is there. So okay, because there is only one slab device. Okay, and here we will write to memory 0x02, and then we will send the value. This is our 2 is our, okay, now is not now is okay 550, but I'm putting the hour as like this. I can also change it. Okay, let me change. Now it is 5 plus, so let me change to 5. No, it should be 5 plus 12, that means 19. 5 plus 12, no, 17. Okay, let the minute be, okay, this, and then second be this, and then okay, this one is day. So today is Sunday, so this one will be in memory location, okay, 0x03, and so this one is index 3, and in memory location 0x04, it will be, this one is 14 means what? 14 means day. Okay, that 14 means that. Okay, 14 means that, and this one is memory location 0x05. This one will be month, so index will be 5, and this one is 0x06, and so index will be 6. Okay, so this one is in memory location 0x06. This one is in memory location 0x05. This one is in memory location 0x04. Okay, like this. Okay, so in this way, okay, we are sending all this, okay, value. This value we are transmitting from this ARM Cortex M processor, which is a master, to this GS1307, which is a slab device, through this SDA line and synchronized with the Cheryl's clock. Okay, synchronous clock, and this, okay, this is the first we send 0x55, and so okay, it will be sent bitwise by putting this value in I2C MDR register, and from bit bit 0 to bit 7 of MDR register, and then this one, okay, first that value will be put here, and then it will be sent in the I2C bus. Okay, and then this value will again send. Okay, and then this is, I changed to, okay, I changed to 17. Okay, the 17 values in binary will be sent, and then this value will be sent, this value will be sent, again this value will be sent, this value will be sent to their respective, okay, this memory, okay, RAM address inside DS1307. So that's the way, okay, in I2C bus it is sending. So thank you all for this session.